So I have a few comments on this. The first one is, I always argued that Q corresponds to the inverse covariance matrix. Now here we have an interesting setting, namely I've constructed the graph Laplacian, in the minutes before the break, as you've seen here. You can construct it in an alternative fashion by saying that the graph Laplacian equals d minus w, where w is a weighted edge matrix, or I should say node-to-node incidence matrix. So if two nodes are adjacent, if you want a pairwise factor between them, then there will be a non-zero element in W, an element larger than 0 in fact, and otherwise not. And D is a diagonal matrix which holds on its diagonal the row sums of W. So 1 is here a vector of 1s, an n by 1 vector of 1s. And by construction, the row sum of L is 0. So L times 1 gives me the 0 vector. And this tells me that we have one eigenvalue of L that is 0. And this in turn tells us that L is singular. So if I consider L as a precision matrix, or as the inverse of some covariance matrix, then very unfortunately I cannot invert it. So we have no Gaussian process with a covariance matrix whose inverse would be L. So there is no Gaussian process or Gaussian random field with a covariance whose inverse would be L. However, there is a related family of stochastic processes, namely stochastic processes whose increments have a Gaussian distribution. And these are called intrinsic random fields. So intrinsic random fields have increments that follow a Gaussian distribution. And so in fact, this graph Laplacian L defines a first order intrinsic Markov random field. Earlier on I said that we want to solve for our latent variables x by solving this problem here, and I have now argued that if we take the graph Laplacian, then actually Q is singular, but we add a little bit of identity matrix to it. And so this entire thing here becomes invertible. And we can obtain a solution. And there are deep links between, what choice precisely of precision matrix you use and what kind of Gaussian process you're talking about. These intrinsic. So if you think of L as being the inverse of the covariance matrix, the fact that we have so many zeros in L means that our covariance matrix, earlier I said that Q is sparse the way we construct it, and Q minus 1, if it exists, is dense. So in other words, we have managed to model long-range correlations, or to model very long-range correlations only through perfectly local interactions. Okay. This was the first comment. And my second comment is about making this whole thing conditional. So conditional Gaussian Markov random fields. The energy function that we had previously written was and we have previously argued in the context of discrete MRFs that it can sometimes, so we don't want to have smoothness assumptions everywhere, it can make sense to encourage label transitions or to encourage non-smoothness when in the image we have evidence of something happening. Yeah? So we can make Q depend on the observations also. And in terms of our famous picture, this is what it looks like. So this makes it conditional. In terms of our famous picture, we now make these factors psi ij also depend on the observations. prettier. And once we have learned the dependence of Q on O, so of course this this dependence must be learned. And it has been a big issue in the literature to see if it makes more sense to learn a prior that is as good a generative model as possible for images, or if it makes more sense to learn this function so that we get out reconstructions that give us a smaller loss, so-called loss-based learning. And this loss-based learning has been the winner in every competition. Okay, it must be learned, and it can either be learned in the maximum likelihood sense, so obtain the best generative model possible for images, or it can be trained by loss-based learning, which means obtain the best, I don't want to call it prior or generative model any longer, so we want to obtain the best model for specific tasks. Such as, denoising or deblurring or whatever it is. Okay, let me delete the word generative up there, please, because it is not a true generative model any longer. Previously, at the beginning of the last session, I had written my posterior, I had decomposed it in terms of a likelihood and of a prior. But if we now make the right-hand side the term, if we somehow make it depend on the observations also, then it is no longer a true prior. It is it now becomes dependent on the observations. Okay, so that means we model the posterior directly. Okay, and today I will not say in detail how this loss-based learning happens, but I want to show you what flexibility people use. So this can now. So what we have here is an entry Qij, which somehow depends on. It could depend on the observations I and the observations j, but maybe you even want to make it depend on more observations. Yeah? So in principle, I could make this element here depend on all observations if I wanted to. If I do that, then I should add more, more lines here. And we have complete freedom of choice of how we want to do this. This functional dependence can be modeled, for example, using classification and regression trees. And I want to show you a famous, or by now famous, paper. This is the decision tree fields paper from Sebastian Novotzin and colleagues. This is from 2011. And here is the model that they use. So, in fact, one of the problems that they wanted to solve was to label body parts of a human who is standing in front of a gaming console. And when we have a human standing in front of a gaming console, we know that the let's say the vertical neighbors have a different meaning from the horizontal neighbors. And accordingly, I've always drawn uniform, I've always used the same potential in a 4 neighborhood. But here you see that they use different potentials. So for example, they use a potential C that connects every pixel with its horizontal neighbor. And they use a potential D that modulates the interaction between a pixel and the neighbor to its bottom left. They have a fairly long range potential E connecting to the second most neighbor to the bottom right, and so on. So this is just to show the schematic, and in fact they've used some pretty long range interactions and have thus successfully solved hard problems like the one that I've alluded to, so this body part labeling here. And this concept has since been developed further. So for example, you can use cascades of such architectures, and much thought has gone into how to learn these Q of O functions efficiently. The problem is that if you want to do this iteratively, every time you change Q, you have to resolve your entire linear system to see if your solution became better or worse, and so on. And because there is a matrix inversion in between, it's not so obvious to see or to understand how a change in Q will affect the final solution. Okay, so these are conditional Gaussian Markov random fields. So far I have been using denoising as an example, and now I want to show you how you can do classification with these. So in classification, one trick you can do is the following, and I'm now switching to plate notation because otherwise my picture is going to be very messy. I have a random variable located at pixel I. I have an observation at pixel I. I shade this node to say that, we have made a measurement there. And this xi is now connected via pairwise factors to its neighbors in the lattice. And now, given the observation, I can also get an estimate to what extent I believe that my particular pixel belongs to a certain class. So I don't have a generative model any longer. Again, I model only the posterior probability. And we have to solve this capital K times if we have capital K classes. So, note that I have n of these nodes, but only k of those. So k, capital K, if I have k classes. So I have introduced auxiliary nodes to my problem. Okay, let me, I'm not so happy with my drawing yet. I will give you 3 versions altogether, okay? In the next version, I'm starting from something you know better. Okay. So because the observations have already been made, I collapse them into their factor. Okay, so I'm going to say that this thing here becomes just a pairwise factor. Okay, because the observation has been made. So the distinction is that I can write this potential as a potential associated with I. It depends on xi. And I can now make explicit the dependence on OI. I would do this if I write this here with a comma, probably. Or I can make it implicit. I just omit the observation O, and perhaps I write a k, superscript k, to say that now I'm asking to what extent my random variable belongs to class number small k. Okay? So down here are my latent variables x, and up here are my meta nodes c. I'm going to use 3 here for a 3-class problem. And now I'm connecting every node to these auxiliary nodes. And the effect of the observations has somehow been absorbed in these pairwise factors. Okay, you get the idea. So these are the auxiliary classification nodes, which I've here called C. And for example, we may have 3, if we have 3 classes altogether, and X were my latent variables, and I have, for example, 1,000,000 of these if I have a megapixel image. Okay, so I have many nodes associated with the pixels, and then very few of these auxiliary nodes.
See the right part again?
Sure. Okay. Can you not read something? Yeah. Yeah, the total number if I have a megapixel image. Okay. And so the question is, how can we solve this? And one possibility is as follows: to simply, say, okay, this is now a somewhat extended Gaussian Markov random field. And in this case, we have some random variables observed. So these are observed. And now I want to find the conditional distribution of the remaining ones. So generally speaking, let's say that this is a graph here with vertices and edges, and I now partition my set of vertices. So I say that my vertices is the set A, it's the union of set A and B, and I say that I want no intersection between the two. And I can now partition my random variables accordingly. I can say that I'm now interested in, so I'm going to say that I'm calling the set of nodes A, these are my variables x, and my set of nodes B are these classification random variables. And I'm now improvising my notation on the go, which is never a good idea. But let's see what this gives. Okay, so I'm going to partition my entire precision matrix into a part. Let's see. I will say, yes, it's a good idea to wait. So let's say my entire set of random variables is the set x and c taken together. And so those are my random variables. And they have a mean, let me call this mu x and mu c. And we have this precision matrix Q, which I'm going to partition into QXX, QXC, QCX, and QCC. Okay, and yes, go ahead.
Why are these random variables?
I treat them as such initially, and then we will make the observations. Okay. So initially I claim that these can take any value they want. In fact, what we will do if we solve for, if I want to infer to what extent all of my nodes belong to one of the random variables, then I will make an assignment. For example, I will make the assignment that this one here is 0, and this is 1, and this is 0. And in that case, when I solve for my x, I compute my estimate that any of my latent variables belongs to the class 2. Okay? So I am now interested in my distribution x given c. This is still a Gaussian Markov random field. And I can find its parameters as follows. I want to minimize with respect to x the following expression. So this is x minus mu x, c minus mu c. Okay, and now I know, so to minimize this, I will differentiate with respect to x, this entire thing, and set it to 0. And what I find is that this qxx times x minus mu x equals minus qxc times c minus mu c. And if I now solve for x, I obtain my conditional mean. So I obtain mu of x given c. And this is now one of the two parameters of my, so I argued that x given c is still a Gaussian Markov random field, namely with parameters mu x given c and with parameters q of x given c. And it turns out that q of x given c is identical with qxx. So the first part of the statement you can really show by just doing this derivative. The second statement is a bit more complicated. I'm not doing it here. Okay, so that means what I need is these elements here. Qualitatively, this is like a coupling strength of every random variable xi to every class k. This is what it models. Okay, so qxc has as dimensions n, if I have n nodes, times capital K, the number of classes. And I'm here demanding that these sum up to 1. So the sum over k qxc some element ik out of it should be 1. And because they sum up to 1, another interpretation is that this is the probability that my sample number, didn't write it in words, it's my unary term that xi belongs to class K. And of course that depends on the observations. This is the dependence that I have somehow omitted by not writing the observations here, even though it really depends on the observations. So that means I can use a classifier like random forest to estimate this number or these numbers. So this thing down here, because the classes themselves are not coupled, is just the identity matrix. and qxx is going to be it is the sum of the Laplacian defined only in the spatial part of my network. And then the minus qxc times 1, where this is again the vector of ones. Okay, and I've made a sign error here. I should say this is the negative probability, and this should be minus 1. And okay, so what have we done? For classification purposes, I have introduced these auxiliary nodes, and we solve this problem k minus 1 times if we have k possible labels, because the solutions will add up to 1. So I've introduced these auxiliary random variables, constructed a bigger Markov random field encompassing both the spatial domain, those were the variables x, and these auxiliary random variables. And now we condition on the values for these auxiliary random variables. So this problem that we see here, we solve it k, or in fact k minus 1 times. One time for c being 1, 0, 0, for c being 0, 1, 0, and if it's just 3 random variables, then we are already done. But in general, so for c being ek, where e is a vector of unit length which has a 1 in the kth position and zeros elsewhere, the kth unit vector. Okay, so for the 3 class example, this is the classes C that I would use. Now, if I did this with a matrix inversion, then I would need to do the matrix inversion just once, and then multiply with all these different vectors. However, I've argued that the matrix inversion turns a sparse matrix into a dense one, so instead you solve the system of equations, the sparse system of equations, k minus 1 times. So this is how you can do classification with these Gaussian MRFs. And the last thing I want to say is that you can use that for seeded segmentation, and that is the so-called random walker algorithm that you will see in the exercises. In the random walker algorithm, you only select nodes, namely those nodes where a user has clicked, to the auxiliary nodes. So we have a sparse connection of the entire network to these auxiliary nodes. And that can be used for seeded segmentation, as in this example from the random walker paper of Leo Grady. In this case, it should be a color image, but 2006 was a time when journals still printed black and white. So let's say label 1 is the red class, label 2 is the blue class, label 3 is the green class, and label 4 is pink. So we introduce 4 auxiliary nodes, a red one, a blue one, a green one, a pink one. And only the pixels which have now been painted in this image are connected to these auxiliary nodes. All other pixels are merely connected to their neighbors. And now we solve the sparse system of equations 3 times, and the solutions are given here. And the 4th solution just follows. The 4th solution is 1 minus the sum of the others. This is the 4th solution. And now we can threshold these images, and the result of the thresholding gives me this partitioning, where really this class here is now the pink one, and that class here is the green one, and that class is the blue one, and that class is the red one. So this is an example of a seeded segmentation algorithm. You see, for example, there is nothing in the image. The image brightness does not allow us to differentiate between the red and the green class. Both are bright. But this is seeded segmentation, where the user says, in this area I want that class to live, and in that part of the image I want that class to live. And this information is essentially propagated through this MRF that we have built. So this is an example of a seeded segmentation algorithm. Seeded segmentation, where the seeds are the things that you see in this image here. Yeah? These are the seeds. Okay. If you have any questions, think about them until tomorrow, because we should finish now. And I will ask for your questions at the beginning of tomorrow. And tomorrow we will look at extensions of this formalism, so how we can go beyond the assumption of Gaussianity and go to models that are truly higher order, so that depend on with factors depending on more than 2 random variables.